everyone, this is Miss List, and today we are taking a look at the first section of Unit 3 in AP Chemistry. This is 3.1, Intermolecular and Interparticle Forces. So, an intermolecular force, we often abbreviate in chemistry as IMF, is an attraction between atoms, ions, or molecules that hold them together. We use IMFs to explain lots of properties about compounds. For example, why carbon dioxide is a gas at room temperature versus water is a liquid at room temperature, and silicon dioxide is a solid at room temperature. We can attribute all of those physical properties of those compounds to the different types of IMFs that they experience. If you've had a chemistry course before, the IMFs that are listed here on the left should sound familiar to you. They often get covered in first-year chemistry courses. The IMFs that are on this side may not be as familiar to you. The good news is that we're going to do deep dives on all of them. First, we have this chart that kind of ranks all the different types of IMFs from weakest on the left to strongest on the right. I was talking about silicon dioxide. The reason it is a solid at room temperature is because it has one of the strongest types of IMFs. If we have something that is nonpolar, like carbon dioxide, it's going to be a gas at room temperature because it has a very weak IMF. And then in the middle, we had water as a liquid, and it's kind of halfway between the IMFs that a solid experiences versus the IMFs that a gas experiences. So this is kind of a summary chart. It breaks down what each type is and how strong it is. But like I mentioned in the intro, we're going to be doing a deep dive on all of them. In this particular section, we get it started with some information about those first three that were on the left, and that's London dispersion forces, dipole-dipole, and hydrogen bonding. So, let's talk about our weakest type of force first, and that is London dispersion forces. Often you see this abbreviated as LDF. London dispersion forces occur in every substance that exists. So they should always be considered. Even if something is inert, like our noble gases, they don't tend to bond with anything, they will still experience London dispersion forces. The other thing to keep in mind is if we identify something as non-polar, this is the only IMF that it can experience. So what is London dispersion force? Well, it's caused by the motion of the electrons within an atom or molecule. As the electrons move around, there's a chance that they are unequally distributed. So, for example, all the negative electrons end up on one part of the molecule. This creates what's called a temporary dipole. That's what makes this a weak force, is because this is a temporary dipole. That negative that builds up on one side will ebb and flow as the electrons continue to move around. And so that's what makes it temporary, is the fact that it can come and go. However, when the dipole does appear, it's going to cause attraction to neighboring atoms or molecules. We're going to look at this picture of what this actually looks like on our next page. Here is an example where we've got a equal distribution where the electrons are kind of all over the place. This would mean that there's no dipole present. But what I was talking about a second ago is that occasionally all the electrons end up on one side. And if they all end up on one side, then that creates a negative side of the atom or molecule. That's what this little symbol is showing, is that's our partial negative sign. And if all the electrons are on one side, then the other side is going to be positive. And if this happens and two atoms or molecules are next to each other, the positive of one is going to be attracted to the negative side of another, and the dashed line, that attraction, is our intermolecular force. Now, again, this is temporary. Occasionally, they're going to go back to these top photos where the electrons are distributed, and then that attraction goes away. So as the electrons move around the atom or molecule, it's going to continually come and go. Now, the ability to form these temporary dipoles has a special name in chemistry, and that's called polarizability. The ability of an atom or molecule to actually do this is called polarizability. Now, the more polarizable an atom or molecule is, the stronger the LDF will be. So what makes an atom or a molecule more polarizable? Well, obviously, if it has to do with the electrons moving around, if we have more electrons, the odds that it's going to happen increase. If your atom, molecule, or compound has a lot of electrons, that's going to increase the strength of this London dispersion force. Another factor that can increase the strength of the LDF is the shape of the molecule. If I have something that has a very long shape, so like a carbon chain, then the likelihood that you're going to form a negative on one end and a positive on another is much higher. If I compare this to something like this, where there's kind of a circular shape, they're all kind of clumped together, it's less likely that we're going to have a distinct positive and negative side. So this would have a weaker F because of its shape. This one is going to have a stronger F. And again, it's because of the shape, we're going to have more opportunities for there to be a distinct positive side and a negative side. Again, this is called polarizability. So if I increase my polarizability, I can increase the strength of the LDF. Our next type that we're going to talk about today is the dipole-dipole force. And it's essentially the same concept as a London dispersion force. The difference is it's not temporary. It is a permanent dipole, and the reason it's permanent is because we're dealing with polar molecules. So the London dispersion forces can happen when I have nonpolar molecules. When it's a dipole-dipole force, that's because I have polar molecules. And we see this example here with the hydrochloric acid. Chlorine is more electronegative, so the electrons are going to be pulled more towards chlorine. And that's why chlorine is the negative and hydrogen is the positive. If I have a second hydrochloric acid molecule, again, chlorine is more electronegative. It's going to pull the electrons more towards its side. And that's what creates our dipoles, our positive with the hydrogen and our negative with the chlorine. Well, if they interact with each other, so two HCl molecules come together, there's going to be an attraction. And again, this is my intermolecular force. That is what is attracting the positive end of one molecule to the negative end of another. And it's kind of like a magnet, if you will. Now, just like there's different strengths of London dispersion forces due to that polarizability that we talked about a second ago, dipole-dipole interactions can be stronger when the substance is more polar. What makes something more polar is if there's a big or bigger difference between the electronegativities in the HCl. So I would have to see the difference in electronegativity for chlorine versus hydrogen, and that can tell me whether something's like really polar or just a little polar. Now, our extremely polar molecules and compounds then fall into a special type of dipole-dipole compound, and that is called a hydrogen bonding. Hydrogen bonding is actually a little bit confusing because it's not a bond like we think of a covalent bond or an ionic bond. It's actually not a bond at all. It's an attraction between. It's an IMF. Now, they get their own category because the electronegativity difference between H and N H and oxygen and H and F, they have a big difference in electronegativity. That means that this bond is going to be superpolar because it's fluorine that does this, oxygen that does this, and nitrogen. They all have to be bonded with hydrogen. That's why it's called hydrogen bond. But I always use the phrase hydrogen bonding is fun, F-O-N-N. These are the only elements that have this superpolar bond with hydrogen. So again, this is a special, super strong type of dipole-dipole that gets its own special name. Now, some things about hydrogen bonding. Just because a compound has a hydrogen or a FO or N doesn't necessarily mean that it hydrogen bonds. The H has to be directly connected to an FO or N. So we see this here in water. Water is supremely polar. So notice in this picture, I have my hydrogen is directly connected to an O. The more electronegative gets my negative end, which is oxygen. My smaller electronegativity value gets the positive end. Two molecules that have hydrogen bonding will be attracted to one another, and the attraction happens between hydrogen and FO or N as well. So notice in this third picture, my hydrogen of one water is going to be attracted to the oxygen of another. Again, this only is a super strong type of dipole-dipole that only happens with FO or N, and the hydrogens must be directly connected. Now, an example of this would be something like this guy. So these hydrogens that are on this side are not going to participate in hydrogen bonding. And the reason for that is because they're not directly connected to FO or N. Neither is this hydrogen. This hydrogen is not connected to an FO or N directly. So this molecule, even though it contains both hydrogen and an oxygen, would have no hydrogen bonding. The hydrogen has to be directly connected to an FO or N. So that's a common misconception that students really struggle with, which is why I made it an emphasis. So now we have a summary of the different types of attractions that we can notice between molecules. Remember, London dispersion happens for everything. So we always have, if you look at this chart, we always have LDF on all of them because everything experiences London dispersion forces. It's the only one that two nonpolar compounds can have. If they're polar, more than likely that's going to be a dipole-dipole is going to be the strongest force of attraction, but it will also have LDF. If I have polar but with a hydrogen directly connected to an FO or N, that's going to be hydrogen bonding is the strongest, which is a form of dipole-dipole, and we know that LDF is always there. One thing that's interesting is if I do have a polar molecule with a non-polar molecule, the polar molecule can do what's called an induced dipole, which means the polar molecule creates a dipole in the nonpolar one. And then finally we have an ion and ion-induced dipoles. These are less common. However, last year's AP chemistry test did ask about an ion-dipole interaction. An ion would be a charged particle interacting with, say, a water molecule, where I would have the negative end of my water attracted to the positive ion. And that would be an example of an ion-dipole interaction. All right, let's look at some practice problems, and then we will wrap up. It says, answer the questions about propene and vinyl chloride shown above. Identify the intermolecular forces present in each one. When we have a compound that only contains carbon and hydrogen, that is a big clue that this is nonpolar. So if I have something that's nonpolar, the only type of IMF that it can experience is London dispersion forces. When you switch out one of the carbons for chlorine, though, we're going to produce something that is polar. And that's because chlorine is more electronegative than carbon is. And so it's going to pull the electrons towards it and create a negative end, which means the rest of the particle will be positive. If we have a polar compound, this is going to be LDF because everything is LDF, and it's going to be dipole-dipole. And then I just need to check, is there a hydrogen directly bonded to an FO or N? There's not, so this is not hydrogen bonding. So part A, done. It says the boiling point of liquid propene is 226 Kelvin, and it's lower than the boiling point of liquid vinyl chloride at 260. Account for this difference in terms of strengths of IMF of present in each liquid. So whenever you have a question like this where they're having you compare two things, you have to talk about both. So I would say that propene has a lower boiling point because it only experiences London dispersion forces, which is a weak attraction between the particles. Why does having weak attraction mean it's going to have a lower boiling point? And you could say something along the lines of weak IMFs allow particles to go to the gas phase easier. Remember, we have to talk about both though. So I would say vinyl chloride has stronger IMFs because it is a polar molecule. This requires more energy to boil. All right, our next type, it says two types of intermolecular forces present in liquid H2S are London dispersion and dipole-dipole forces. Compare the strength of the London dispersion forces in H2S to the strength of the London dispersion forces in H2O. First, let's draw them. Water, and then H2S is going to be very similar, except we switch out the sulfur for oxygen. Now, they only want us to compare the LDFs. When we talk about LDFs, the term we want to use is polarizability. And there were two things about polarizability that affected the strength of the LDFs. And one was the shape. Well, both of these have the same shape, so shape isn't going to help us. The other was the number of electrons. And I think that's where we need to go here. Sulfur has more electrons than oxygen does. So I would say that H2S has stronger LDFs because it has more electrons than, because sulfur has more electrons than oxygen, which makes it more polarizable. Next, they want us to compare the strength of the dipole-dipole forces between them. Well, I'm not going to redraw them, but the big thing about water is that water hydrogen bonds. And so H2S would be a regular dipole-dipole interaction, and then water is going to be a hydrogen bonding situation. Now, what makes hydrogen bonding stronger? It's the big electronegativity difference between H and O. So I would say H2O has a stronger dipole force because it has a greater difference in electronegativity, leading to a, between H and O compared to H and sulfur. You could also write a sentence that explains that the hydrogen bonding is a stronger IMF than the dipole-dipole, but we still would go back to that difference in electronegativity to justify it, because if you don't, you haven't fully answered the question. All right, here we've got consider bromine versus chlorine gas. What forces do they both exhibit? Justify your answer. Well, both of these are compounds bonded to each other. which means they're going to be nonpolar. And the only IMF that nonpolar compounds experience is LDF. So LDF, because these compounds are both nonpolar. And LDF is the only IMF, intermolecular force, that nonpolar compounds exhibit. Which has the stronger of the LDFs? So again, when we talk about LDFs and their strength, we're talking about polarizability. Which one is stronger is going to be about shape and the number of electrons. Well, both of these are going to take a linear shape because it's just they're one bond connected to each other. So, the shortest distance between 2 points is a straight line. So they're going to have the same shape. It has to do with the electrons. If I look on the periodic table, bromine is in the row below chlorine. And that means that bromine is going to have more electrons. I'm going to say Br2 has a stronger LDF than chlorine 2 because it has more electrons than chlorine, making it more polarizable. And then final question here, which do you expect to be a liquid at room temperature? In general, we think of gases as having weak IMFs, and we think of solids as having very strong IMFs. So which one would be a liquid is going to be in between, like the weakest or the strong. We just said that bromine is stronger than chlorine. Out of these two, chlorine, I'm probably going to expect that it's a gas. Bromine, though, because it has a stronger IMF, it's going to be a liquid. And then I need to be able to explain why. So I'd say Br2 will be a liquid because it has stronger IMFs, making the particles harder to separate and enter gas phase. All right, that is 3.1. I hope that you enjoyed it. Again, if you've had honors chem, this was probably a little bit of a review or a brush up. Those other IMFs that we introed at the very beginning will come up in later sections. All right, have a wonderful day.